Every time you search on Google, billions of web pages are ranked in fractions of a second. At the heart of this magic is PageRank, a clever algorithm invented by Larry Page. But computing PageRank efficiently across billions of pages isn't easy. Today, let's explore how MapReduce and Spark make this possible. Think of the web as a giant graph. Pages are nodes and links are arrows. PageRank imagines a random surfer who clicks on links forever. A page is important if many important pages link to it. Mathematically, this boils down to finding the principal eigenvector of the web's transition matrix. Of course, the web isn't neat. Dead ends and spider traps break the math, so we add a little randomness. With some probability, the surfer teleports to a random page. That guarantees convergence. To compute PageRank, we don't solve giant equations directly. Instead, we use power iteration. Start with a guess vector and repeatedly update using the formula until ranks stop changing. Typically, 30 to 50 iterations are enough. Sounds simple, right? The catch: the web graph has billions of nodes, but each page links to only a few others. That means we have a sparse matrix too big for one machine. We need distributed systems like MapReduce and Spark to spread the work across many computers. In MapReduce, each page contributes a fraction of its rank to outlinks. The map step emits these contributions. The reduce step sums contributions for each target page and applies damping. Each iteration is one MapReduce job, repeated until convergence. MapReduce has overhead, that is, job startup and disk I/O every iteration. To improve efficiency, use combiners to aggregate locally before shuffling. And use block partitioning. This is done by breaking matrix into K by K blocks, so you reuse graph data while streaming smaller parts of the vector. Spark handles PageRank differently. Instead of launching a new job each time, Spark keeps the graph in memory and caches intermediate results. That cuts down overhead and makes iterative algorithms like PageRank much faster. Spark also lets you broadcast the rank vector to work as efficiently. MapReduce is robust and good for disk-based pipelines, but slow for iteration. Spark is fast, but needs enough memory and careful tuning. Key considerations include partitioning the graph, reducing shuffle traffic, handling dead ends, and checkpointing for fault tolerance. Now that we've seen the big picture of how PageRank works, let's look at what it actually looks like in code. We'll start with a MapReduce version, which splits work into map and reduce steps across a cluster. And then we'll see the Spark version, which runs the same math in memory for much faster iterations. This is PageRank in MapReduce form. In the map step, each page splits its rank across its outlinks. For example, if page A has rank R under A and 2 outlinks, it sends R under A over 2 to each. In the reduce step, all contributions to a page are summed, and we apply damping with beta plus a teleport term. Each iteration is one MapReduce job. Here's a tiny 4-node graph. A links to B and C. B links to C. C links to A. And D links to C. We initialize ranks equally, then run a few iterations. Here's the Spark version. It looks similar to MapReduce, but Spark keeps the graph in memory instead of reloading it each time. Each iteration, we use flat map to emit contributions, reduce ed by to sum them, and map values to apply damping. The key advantage is speed. The loop runs in memory, not as separate jobs. This is a Spark-like imitation in plain Python. The logic is almost the same. Share rank across outlinks, then sum, and apply damping. In real Spark, the graph is cached across workers and the rank vector can be broadcast. But the math is identical. Only the system handles it more efficiently. And that's it for this video on efficient PageRank computation with MapReduce and Spark. We saw how PageRank works, why distributed systems are needed, and how MapReduce and Spark approach the problem differently. Thanks for listening, and have a great day.